Alright, 4.6, negative and zero exponents. What we're looking at here is a review of the grade 9 concepts and exponents, plus two more laws that we're going to be looking at today that involve exponent laws. Those two new laws are going to be negative and zero exponents, so they're the last two. On this page here, I'm going to list all the different exponent laws that you had to have known up to this point. If you don't remember them from grade 9, well, you might need to spend some time reviewing these concepts so that you have an idea how to answer the questions that follow this example and follow this page. Exponent laws for multiplication is the following. Okay, if we have two powers, now these are known as powers. The bottom is called the base, the little number in the corner is called the exponent. So if I take a power and I multiply another power with the same base, now keep in mind the base has to be the same. What I can do is keep that same base, so yes, this stays the same base, and what I can do is with the exponents I can add them. What that means is if I have, for example, and I'll just show you an example, if I have 2 to the power of 3 and I multiply 2 to the power of 5, because I have two powers with the same base, or let's make that an 8 since it looks like an 8. Let's just look at that a second. It looks like an 8. If I have 2 to the power, let's erase that for a second. Alright, 2 to the power of 8, for example. 2 to the power of 3 times 2 to the power of 8. What will that equal? Well, folks, that's going to equal 2, because again, we share the same base, to the power of 3 plus 8, which makes it 11. So that's an example of exponent law for multiplication. All right, next, we're going to look at the next one. So each example, I'll show you an example of each, but then quickly erase it so we can have all the laws on one page. The next law is exponent law for division. Exponent law for division is as follows. So let's look at this. A to the power of m divided by a to the power of n, or it could be written as a to the power of m over a to the power of n. What will that equal? Well, in this case, what we're doing is we have the same two different powers with the same base, and what I can do is keep the base and subtract the exponents. So an example of that, just quickly, let's say 3 to the power of 5 divided by 3 to the power of 2. What will happen? Well, there are two powers with the same base, means I can keep the same base and subtract the exponent. So I will take 5 and take away 2, and that will give me 3. So once again, it is two powers, so we're looking at the question here. So we have two powers being divided that have the same base, okay? And what we're going to do is subtract the exponents, and we end up with 3 to the power of 3. All right, let's moving on. So let's erase this and move forwards. Next one. Before I forget, keep in mind that the denominator, the base a, cannot equal 0. Why? Well, that would mean that this denominator is 0, and we know that any fraction, or every fraction, is undefined when the denominator is 0. So that's very important to note. Moving on. Power law is the following, where you have a base with an exponent raised to another exponent. This is called power of a power. So the base with an exponent, so that's a power, and it's raised to another exponent. What will this law say? Well, it says that a is equal to m times n. Let's look at an example to illustrate this fact. Let's use a base of 5 to the power of 2, all raised to the power of 3. What does that do for us? Well, I can now take the two exponents and multiply them to get 5 to the power of 6. That's right. 2 times 3 will give us 6. 5 to the power of 6. And then you would go and evaluate if you had to. All right, let's erase this. And we'll move forwards on to another power law or exponent law that we learn. The next one is power of a product. Power of a product says I can take a product and raise that all to an exponent. What will result? Well, this exponent can actually be shared by each individual part of the product. So A will get the exponent, and so will B. How does that help us? Well, let's look at an example. If I have, for example, this time we're going to make it unique, I have 2x, and it's all raised to the power of 3. So we have a product inside here, and it's all raised to the power of 3. The brackets say that this 3 affects everything that's inside. That is different from writing this. So it's not equal to 2x to the power of 3. That's different. This 3 right here, you'll see, is affected only by the x. So this affects only the x. Whereas this 3 affects what's right before it, which is the bracket. That means everything inside there is affected by it. So definitely that's not true. So what will this answer actually be? Well, the 2 will get the exponent 3, as will the x get the exponent 3. So our answer will be 2 to the power 3, which is 8x cubed. So there's an example of where this power of a product works for us. This is an important one because it's used quite extensively in algebra. All right, let's moving on again, moving forwards. Where are we going next? Well, we need another law. Power of a quotient. Power of a quotient, a over b to the power of m. Note that the denominator here, folks, cannot be 0, again, because it would be undefined. But what happens here is the same that happened when it was a product. You would apply the exponent to both the numerator and to the denominator. An example of that, here we go, is, let's say I was to do the following. 2 over 3 all to the power of 4. What does that mean? Well, that means that 2 will get the exponent 4, as well as the bottom will get the exponent 4. So both the numerator and the denominator get that exponent. And if you were to simplify it, because the question asks you to evaluate, you would end up with 16 over 81. So again, you take the exponent and you give it to both the numerator and to the denominator, because that is what a power of a product allows you to do. All right, moving forwards, we're going to erase this example and we're going to move on. The next part we're going to look at is the two new laws that I'm introducing. First one, again, we talked about this, so I don't need to reiterate that. Zero exponent law says the following. Anything, and I mean anything with the exception of 0, to the power of 0 is always equal to 1. That's right, folks. Now, this is the reason why. Let's look at an example where you can understand this concept. Now, keep in mind, very important, important that the base is not equal to 0. So here's an example of why that's the case. I'm going to show you an example. 2 to the power of 3 over 2 to the power of 3. If I used the exponent law for division, that will give me 2 to the power of 0. And I know all of you would agree with that statement, because I'm using exponent law for division, and it says that I can subtract the exponent, so I get 2 to the power of 0. How come this is also equal to 1? Well, let's move backwards for a second and see what happened. So I'm going to erase the 2 to the power 0. Now keep in mind that was also 2 to the power 0. What is 2 to the power 3? Well, it's 2 times 2 times 2, which is 8. And the bottom would be 8. What is 8 divided by 8? That's right, folks. You guessed it. 8 divided by 8 is 1. So, 2 to the power 3 over 2 to the power 3 is equal to, when it's expanded, 8 over 8. 8 over 8 is equal to 1. So it cancels each other out to give us 1. Remember what we had earlier for 8 divided by 8. It was actually, what did we have as an alternative? We had 2 to the power of 0. That's right, folks. That is the miracle of the zero exponent law. The zero exponent law says that any number raised to the power of 0, with the exception of obviously 0, the answer is always 1. And this is your reasoning as to why it equals 1. Basically cancels everything out. So we have 1. Interesting. All right, so we're going to erase this and we're going to move forwards. Next one, the last law. The last law is known as the negative exponent law. The negative exponent law says a to the negative m equals something. What does it equal? It equals 1 over a to the power of m. Why? Because see this negative right here? He's very, very little right here. This negative actually is an instruction. It's a rule. That instruction is the following. Flip, you got it, flip the base. You will always, whenever there's a negative in the exponent, only in the exponent, folks, when there's a negative there, you take that negative and you literally flip the base. So a gets flipped over to become 1 over a. And that exponent now changes to a positive. And then you would normally apply the power of a quotient law so that the m goes to the top and the bottom. And this is an important feature that you have to remember when we're working with exponents. Okay, now on to examples. Example 1, evaluate the following. So we have a bunch of different examples here that we're going to find the answer to. And let's go through them. Here we go. The first one, 5 is raised to the power 0. What's that answer? That's right, it's just 1. What about 1 over 5 to the power 0? That's right, the answer is still 1. Anything to the power 0, with the exception of 0, is 1. Let's go to the next one. 3 to the negative 1. What is that? The negative exponent law says 3 gets flipped, becomes 1 over 3. Now, let's just hold on. That's too much info right here. We're going to move slowly through this. So, 1/3. So the 3 flips itself, it becomes 1/3, and it raises to 1. Next, we simplify this expression because we have to evaluate. We need a final answer. That's going to be 1 over 3. All right? So this exponent 1 gets applied to the numerator, and to the denominator we get 1/3. Moving on. Negative 2 to the negative 3. What does this mean? Well, this negative, not this one, folks, but this one up here, says that we need to, that's right, flip the base. Now, when we flip this base, keep in mind that when we flip it, it becomes negative 1 over 2. Why? Because the negative, this negative actually is not attached to the 2, but it's attached to the side. It's always attached to the numerator of any fraction. When it's a whole number, it's just the number. But when it's a fraction, it's always attached to the numerator. Now, this is now raised to the power of 3. Now, let's go over why the answer is negative 1 over 8. Negative 1 is raised to the power of 3. The negative gets 3 negatives. Negative, negative, negative. That makes a negative. 1, 1, 1 multiplied by each other stays 1, so it's negative 1. On the bottom, it's 2, 2, 2, 2 times 2 times 2, and that gives us 8. So that's why the answer is as it is. Moving forwards, part E. 1/9. 1/9 gets flipped to become 9. That's right. It's not 1/9, but actually flip the base, and that becomes 9/1, which is just 9 to the power of 1. What's the final answer? That's 9. And yes, folks, you could actually skip and go right to this answer, and you will get the full marks. This is just showing what happened from here to here. Next, 3/4 to the -2. Flip it to become 4/3. Because of the negative, we flip the base, 4/3, all to the power of 2, and we evaluate it to give us 16 over, now 4 to the power of 2 is 4 times 4, and 3 times 3, that's right, is 9. And let's look at the last two. 0 to the power of 3, that's 0, 0, 0, 3, and 0 times 0 times 0 is 0, folks. But when we have 0 raised to the 0, we don't know which one is more important. Is the 0 as the base more important, or 0 as the exponent more important? Because we would have two alternate different answers. Well, that becomes a question that can be later on answered in calculus, but at this point in grade 10, we're going to focus on the answer, which we would say it's at this moment, it's undefined, or you can say that the value does not exist at this point. Moving forwards, we're going to look at example number 2. You all know that we're going to focus on a word problem, so there has to be some sort of word problem that applies to exponents. So here it is. Carbon-14 is a radioactive element that decays to 1/2 or 2 to the -1 of its original amount after 5,700 years. Determine the remaining mass of the 10 grams of carbon after 11,400 years and B 28,500 years. So how are we going to do this? Later on in grade 11 and grade 12, we learn about formulas that involve decay. Here, we're going to discover how we can use exponents to answer this question. Well, I want you to note that 11,400 years divided by 5,700 years happens twice. That means the number of terms, or the number of 5,700 years, or number of periods, is 2. So twice the mass gets halved. So how do we look at this? Well, it's half of the amount. How many times? That would be twice. Half the amount twice of the 10 grams that we started with will equal the amount after a certain amount of time. That amount of time will be 2. So the amount of time, we could change that t to be 2. So the amount after 2 cycles of 5,700 years will equal 2.5 grams. So there will be 2.5 grams after 11,400 years. Let's look at the next one, 28,500 years. You take the number of terms will be 28,500 years divided by 5,700. Lucky for us, it turns out to be a nice number. It's not always a nice number, folks, so you might have to sometimes use a fraction. But in grade 10, you can probably guarantee I'm going to give you a nice number, or relatively nice number. So what are we calculating? Well, the amount after a certain number of time, and that time, okay, and keep in mind, I'm going to just show you this quickly to you. That amount after a certain number of time is after 5 times will be 10 times 1/2 to the power of 5. So the 5 gets applied to the whole half. That becomes 1 to the 5 times 2 to the 5. And if you type this in your calculator, you will get 10 over 32. And if you typed it all in your calculator, you would have gotten 5 over 16 as a reduced fraction of 10 over 32. Now, are you allowed a decimal for this question? Yes, you are. You should really only work with decimals if they are nice values. That means they terminate, they stop, they end at a certain place. and 4 decimal places it ends, thankfully for us, because that is the minimum number of decimal places I would want rounding, and so we get 0.3125 grams. So this is how much is left after 28,500 years. On a side note, keep in mind, this is not something that's just a random thing that we talk about in math. This is real life. Radioactive element remains radioactive even after 28,500 years. There is still a radioactive portion of an element. So the question is, does it really ever disappear? And that's something that all of us have to understand. Anyways, that's an ecological problem, or a physics problem, or a chemistry problem, and we just wanted to know the value. Alright then, that's the end of the video. Have a great night. Have a numerical day. Take care.